All right, so this is the section 8.1, Similarity in Right Triangles, and I am with about 8 students in my Block 5 class. You want to give a shout out, Block 5?
Nah.
No. Nah.
Okay, they're kind of lame, but okay, let's take a look at this section, 8.1, Similarity in Right Triangles. Colin, this is my lucky pencil. I want this back.
Well, I'm going to be a lucky person.
Okay, so in a right triangle, an altitude drawn from the vertex of the right angle to the hypotenuse forms two right triangles. So we're starting off with this theorem, 8-1-1, which says the altitude to the hypotenuse of a right triangle forms two triangles that are similar to each other and to the original triangle. So what I want you to understand from this is when you have a right triangle, we're starting with this right triangle, ABC. We see that angle C is the right angle here. If you draw an altitude to the hypotenuse from the right angle, this is an altitude forming another right angle here, we now have not just one right triangle, but three right triangles. We have, I'll call it the big one. It's kind of like a Papa Bear, Mama Bear, Baby Bear. We got the big one here in blue. We have the medium one here, which I will put in red. And then we have the baby one over here. Okay. And what's special about these three right triangles is that they are all similar to each other. Okay, we just spent a whole chapter on similarity, so I know you know what that means. And if I ask you to put the letters in the correct order, I mean, obviously you can see what it is here, but I want you to understand if I say I want to go from the big triangle, I'm naming this A to B to C, do you notice that I went from like the smallest angle to the medium angle to the right angle? Would you agree with that? Okay, or you could say if I went from A to B to C, I went across the hypotenuse first, then did I go across the long leg or the short leg next? Short leg, and then I finished up with the long leg, right, in that order. So without looking at these, I'm scribbling these out, without looking at these, if I'm talking about the medium triangle now, that's this one, in what order should I put the letters so that it's going to be similar to triangle ABC? Well, again, I want to do the same pattern. I want to go across the hypotenuse, short leg, long leg, but except on this triangle. So in what order should I put the letters, Jacob?
The ADC.
ADC. Do people agree? If I go A to D, I'm going across the hypotenuse. Is that true?
Oh, wait, no.
No, it's ACB. Ooh.
I've got to go to the
All right, let's see. You want to ACD. Now, if I go A to C, am I going across the hypotenuse?
Yes.
And then from C to D, am I going across the short leg?
Yes.
Like we did before? And then D back to A would get us back to across the long leg. Okay, then what about this tiny triangle here? With this triangle, what order should I put the letters if I want to, again, go across the hypotenuse, then the short leg, then back to the long leg, because that's the pattern that we established with triangle ABC. What do you think, Colin?
It's going to be CBD.
C to B goes across the hypotenuse of that, and then B to D. C, B, D. Does everybody agree with that? All right, and let's see if that is what I had written here. A, C, D, C, B, D. Are we okay with this? Okay, so now that you've done that, I'm going to ask you to do the same thing with this example. So you have, let me start us off by saying, let's start with triangle, I'm going to call it KLJ, just to get a little different order here. And I want to know, whoops, what, if we're starting with triangle KLJ, that's going to be similar to what triangle? Similar to what triangle? Can you put the letters all in the right order? Again, we're looking at a big right triangle, a medium right triangle, and a small right triangle, but they're all similar to each other. And for the first triangle, we are saying K to L to J, like this. All right. Did I go the same order as I did last time? Or different? All right, Jacob.
Would K, J, and U.
K to J to M. Do people agree? K to J to M. So that's going across the hypotenuse, and then the short leg, and then back along the long leg. Is that the pattern that we had started here with K to L? That's the hypotenuse. Then to J is the short leg, and so on. All right, what about this last one, Stephen?
J to L.
In this little one here, you're saying you're going to start with what?
J to L.
Do people agree with that?
Yes.
J to L is the hypotenuse, L to M is the short leg, and back again. All right, so they said LJK.
Ooh. Oh, we did.
So are we all, did we do everything wrong?
No.
No.
They skipped through us.
They went L to J to K. We went L, we could do the same thing if we go L, J, then K, right? Is that the same here? J, M, K, J, M, K, right? Like this? And L, M, J, L, M, J. So I think we all have the letters in the same order? Okay. All right, so Lady Liberty holds a tablet in her left hand. The tablet is 7.19 meters long. And why do I have this on here? Did we do that one? That was weird. That just popped in there for no reason. Okay. I'm like, why is that in this section? Okay. Consider the proportion A is to X as X is to B. In this case, the means of the proportion are the same number. I don't know if you've heard that when you set up a proportion, like let's say 2 is to 3 and 6 is to 9, would you agree with that proportion? These numbers here, this denominator and this numerator here, are called the means. All right. Those are the two means. All right. And these numbers here, the 2 and the 9, would be called the extremes. Have you ever heard that before? No? Okay. So you've been using proportions for many years, but maybe you didn't know that they had actually, some actual terms associated with the pieces of the proportion. Okay, so the means of this proportion, A is to X, as X is to B, the means are the same number, right? They're both X, in this case, whatever it is. So that number is called the geometric mean, all right, of the extremes. All right, so in other words, if I say, let's say 2 is to 4 as 4 is to 8, is that a true proportion? Yes? So do you see that my means are the same here? So this means that the mean of 4, this is the geometric mean of 2 and 8 would be 4 in my example. All right. Let me slide all this down so I can write that.
Yeah. What's
Stop that.
the exact definition of it for geometric?
Well, we're going to get to that in just a second.
Oh.
Let me just say for this example, 4, I'll say so, 4 is the geometric mean of 2 and 8, all right? It is the number that you would multiply by itself so that you would get the product of 2 and 8, okay? All right, so the geometric mean definition is here. The geometric mean of two positive numbers is the positive square root of their product. So is it true that 4 is the square root of the product of 2 and 8? What's the product of 2 and 8? 16. And what's the square root of 16? 4. So that's why 4 is the geometric mean of 2 and 8, because it is the square root of the product of 2 and 8. All right? So let's take a look at, so they have it here. So the geometric mean of A and B, where am I at? So the geometric mean of A and B is the positive number x, such that x is the square root of A times B, or you could write that x squared equals A times B. All right, so let's try, and you're getting some of this written down on your tool belt, right? Well, I think that they're both part of the definition, I think. This is kind of giving you a formula to find it. This is kind of telling you what it is in general. Okay, so in this example, find the geometric mean of each pair of numbers. If necessary, give the answer in simplest radical form. So we're going to be, practicing simplifying radicals again today. All right. So let's try this first one. If we want to find the geometric mean between 2 and 8,
It's 4.
well, we already knew that one, right?
Oh.
Hey.
Oh.
All right, that's 4. All right, what about the geometric mean between 10 and 30? You got some choices in how to figure this out. You can say, all right, that would mean 10 is to x as what? As x is to 30, which means that x squared has to equal what? 300. And then to get the answer for x, we need to do what? Take the square root of both sides. Technically, we would need, whenever you take the square root of both sides, you need plus or minus. But since our definition said the geometric mean is the positive square root, so we don't really need to worry about the negative in this case. So we get x equaling the square root of 300. Can we simplify that? Do I still have, look at that, I still have my list. People that are watching this video can't see, but I have my list of perfect squares next to the smart board. And what perfect square divides into 300?
100.
All right, so I can rewrite this as 100 times what?
3.
So square root of 100 times square root of 3, so my answer should be what?
About 10.
10 times the square root of 3?
10 red, 3
Do we agree? So that 10 square root of 3 would be the geometric mean between 10 and 30? It is. All right, what about the geometric mean between 8 and 9? Can you work on that one, please? All right, how are we going to set this one up, Jacob?
Put an equal for x.
8 is to x as x is to 9. That means that, good morning, that means that x is the geometric mean between 8 and 9.
X squared.
So x squared equals 72.
Square root.
All right, take the square root and simplify that, please. Okay, so we are finding the geometric mean between 8 and 9. We said 8 is to x as x is to 9, so x squared equals 72. Did you then take the square root? So you got x equaling square root of 72. Is there a way to simplify that, or is that in simplest form already? What do you think? Emily? 6 squared. How'd you get 6 squared root of 2? Oh, and it simplified it nicely for you? All right, so, but what perfect square goes into 72? Mackenzie? 4 goes into 72, so you could split it up into 4 times what? 18, so that would give us 2 times the square root of 18. Any perfect squares that go into 18? For those of you watching at home, our perfect squares, 1, 4, 9, 16, 25, 36, 49, 64, etc., etc., etc. What goes in? What goes into 18 that's in the list? 9. So I could write this as 2 times square root of 9 times square root of what? 2, right? 9 times 2 is 18. And square root of 9 is what? 3. So I get 2 times 3 times square root of 2, which is 6 rad 2, which is what Emily told us. And we could have gotten Emily's answer directly by choosing a larger number than 4. What? 36 goes in, so I could write square root of 72 as square root of 36 times square root of 2. That's 6 times the square root of 2. Either way, we get the same answer. Are we okay with that as the geometric mean?
Wow.
Between 8 and 9.
Yes.
Is that what we have? All right, moving on. You can use theorem 8-1-1 to write proportions comparing the side lengths of the triangles formed by the altitude to the hypotenuse of a right triangle. All of the relationships in red, which I have covered right now, involve geometric means. So I kind of wanted you to write these proportions. Notice they've taken the right triangles that we were working with previously, the big right triangle, the medium right triangle, the little right triangle, those three right triangles which are all similar, and they've kind of named some of the sides. So they're calling this side B, they're calling this side A, the big side is still C, all right, but then they're also calling the altitude to the, to the right angle, they're calling that H, and they're calling this little piece of the big hypotenuse X, and they're calling this larger piece Y. So with that in mind, we want to see ratios set up equal to each other. So B is to A. So I want you to think B is to A is that hypotenuse over short leg over long leg. What is that? All right, so that they have established a pattern where they're going to take long leg over short leg. Everybody agree? No, they didn't. They were doing nothing with the hypotenuse right now, right? So in the large triangle, long leg over short leg would be B over A. What would that be if we were looking at the medium triangle here? Y over H. Do people agree? That's going to be the long leg over the short leg. All right, Y over H. And what about in the little triangle over here? Hands, please. Long leg over short leg would be what, Anna?
H over X.
H over X. Do people agree that that's the long leg? This is the short leg? Equals H over X. Okay, so I have Y over H, H over X. Looks good. Notice when we set up this part, they said in red, Y over H equals H over X. Since we have the same number here as here, what do we call H? The geometric mean of what and what?
Y and X.
Of Y and X. So H right here is the geometric mean between this piece of the big hypotenuse and this piece. Does that make sense? Awesome. All right, so let's try this with this, what else do they have? Oh, right here. Let's try C over A. If we're doing C over A, that's not what I wanted to do. That's all right. I'm just trying to move this maybe out of the way a little bit. Okay, so if I want to do C over A here, where's C over A? Let me go back to my original picture, which I can clean up a little bit. If we're talking about C over A, is that short leg over long leg over hypotenuse? What is that? Jacob?
Hypotenuse over short.
All right, so they're establishing a pattern that we're going to use hypotenuse over short leg, right? In every right triangle, there's a short leg, a long leg, and a hypotenuse, right? Okay, well, not in every right triangle. I should say in every non-isosceles right triangle, because if it's an isosceles right triangle, the short leg and the long leg are both the same length. You with me?
Absolutely.
But if it's not an isosceles right triangle, there's going to be a short leg, a long leg, and a hypotenuse. So in this picture, we have hypotenuse over short leg would be C over A. So I'm asking you to come up with the pattern for that in the medium triangle and in the small triangle. Now they've rewritten the medium triangle and the small triangle here, but you often will not have this written on your
I
paper.
don't like that.
Yeah, I'm with you. I think that's confusing. I like to just look at the original picture and focus on the medium triangle, focus on the little triangle, and so on. So would you take a minute, please, and see if you can write out what the other two ratios would be, one for the medium triangle and one for the small triangle. Okay, so what did you get for the hypotenuse over the short leg in the medium triangle? Aaron?
B over H.
What was it?
B over H.
B over H. Do people agree? In the medium triangle, B is the hypotenuse and H is the short leg, so B over H And then what about in the small triangle? What do you think, Colin?
A over X.
A is the hypotenuse and X is the short leg, so we're going to say equals A over X. All right, so notice they have C over H, I'm sorry, C over A equals B over H equals A over X, but the part in red here, the C over A equals A over X, I should do that in red just like they have. C over A equals A over X. What do you notice about that proportion right there, Michael? What's the geometric mean? If we're looking at this. A is the geometric mean. A is the geometric mean between what and what? Or geometric mean of what and what? C and X. So let's look at our picture and focus on what they're talking about here. Cleaning this up a little bit. So they are saying, or what we've noticed, is that A, right here, this short leg of the big triangle, right, is going to be the geometric mean between X, which is this little piece of the hypotenuse, and C, which is the whole hypotenuse. So we've got another way of finding side lengths in these similar right triangles, right? We've got the fact that this short leg of the big right triangle is going to be the geometric mean between this little piece and the whole thing. All right, one more. Let's do this one. We've got C over B. So in the big triangle, what is C over B? Is that short leg over long leg, hypotenuse over short leg? What pattern is that, Anna? Hypotenuse over long leg. Do people agree? C is the hypotenuse, B is the long leg. So hypotenuse over long leg. All right, and can you come up with the hypotenuse over long leg for the medium triangle and one for the small triangle? We want hypotenuse over long leg. What do you think, Colin?
It is C over B, B over Y, and A over H.
Wait, it's too fast for me. B over Y.
B over Y.
B is the hypotenuse of the medium triangle, over Y is the long leg. B over Y, and then what about in this little triangle?
A over H.
A is the hypotenuse, and H is the long leg, equals A over H. So we have B over Y, A over H, and notice the part in red was here. So if C over B equals B over Y, then what is the geometric mean of what, Stephen?
Geometric mean of A over H.
We're right here. B is the geometric mean of, what are the extremes of that proportion? Remember, these are the means. B is the mean of what?
C over Y.
All right, so we're going to say B is the geometric mean of C and Y. So we have B is the geometric mean of C and Y. A is the geometric mean of C and X. And we already said earlier that H was the geometric mean of X and Y, right? From this one right here. So let's look at this one for a minute. B is the geometric mean. We're focusing on this one right here. B is the geometric mean of C and Y. So looking at our big picture here, let's see what that means. B, that's this long leg right here, is going to be the geometric mean between C, which is the whole thing, and Y. So between this piece of the big hypotenuse and the whole thing. All right? Okay. So that is stated here in the these corollaries, the geometric mean corollaries. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the two segments of the hypotenuse. The length of the altitude to the hypotenuse of a right triangle. They're talking about this segment right here. That is the altitude to the hypotenuse. And that segment, which we're calling H in this picture, is the geometric mean of the lengths of the two segments of the hypotenuse, right? So that means that H is going to be the geometric mean between, I should color code this, that H is the geometric mean between X and Y. Does that make sense? That's our first proportion. We already learned that on the previous page. All right, and then corollary 8-1-3 says the length of a leg of a right triangle is going to be the geometric mean of the lengths of the hypotenuse and the segment of the hypotenuse adjacent to that leg. This is not anything new. This is exactly, I'll come right back to this page, that's exactly what we were saying here and what we were saying here. All right, that's exactly what we had discovered on this page. All right, this is it just written out formally as a corollary, okay, to our theorem. So that means in this picture that A squared, so A right here, this short leg, if you will, is the geometric mean between this little piece, color code this, between this little piece here and the whole thing, which is C. Does that make sense? Likewise, we could talk about side, long leg B. Long leg B, where is it? Right here. So long leg B is going to be the geometric mean between what and what? B, this long leg, is going to be the geometric mean between what two segments in this picture? Between C, which is the whole thing, and what other segment? Y, the little piece of the hypotenuse that's adjacent to that leg. So B is the geometric mean between Y and C. Okay? So this gives you a way of finding out side lengths in a right triangle. All right? Okay. And I'm moving on. So if you did not get these, you're going to want to copy those out of the book. Okay. So measurement application. Here is Big Tex. I guess he's been at the Texas State Fair since like 1950 or something like that. To estimate the height of Big Tex at the State Fair of Texas, Michael here steps away from the statue until his line of sight to the top of the statue and to the bottom of the statue form a 90-degree angle. You getting that? So the angle formed from the top of the statue to Michael's eyes down to the bottom of the statue, that's a right angle.
What?
No,
Michael's eyes are 5 feet above the ground, so maybe he's like 5'3" or
So
something.
he's 15 feet away.
He's 15 feet away. All right, yeah, let me finish reading. His eyes are 5 feet above the ground, and he is, were you thinking he was 15 feet tall? No, no. Michael is not to be confused with Big Tex, okay? All right. So his eyes are 5 feet above the ground. So his eyes right here to the ground are 5, which is why this segment right here is 5. And he is standing 15 feet 3 inches from Big Tex. So this distance from here to here is 15 feet 3 inches. All right, and we are trying to find the height of Big Tex to the nearest foot. So in this example, they're saying let X be the height of Big Tex above eye level. So in other words, they're saying let's just make from here to here, let's make that X. Agreed? And when we solve for X, we'll have to add on this 5 to get the height of Big Tex. So they're saying X here, no, let's see. They're saying this 15 feet 3 inches is going to be the geometric mean. So I'm going to put 15 feet 3 inches. Actually, how many, let's convert to inches. How many inches is that? Oh, man. Or, well, it's up to you. We could convert to feet too if you like. Which would you prefer? Inches? So 15 times 12 is what? 180. So is it 183? All right, so 183 is the geometric mean. So I'm putting 183 here and here. Is the geometric mean between what and what in this sketch?
Between 5 and X.
Between 5, which is this piece right here, and X, which is this piece right here. That's the proportion that you need to solve. Would you do that, please? Or is it already done for you? Well, no, they use different numbers because they're using feet, we're using inches, so you're going to get a different answer.
Wow.
What'd you get? Your lucky calculator? All right, so we're getting 5x equals 183 squared, whatever that is, and x turns out to equal what? 6,900?
6,697.8.
All right, and so can we convert that to feet by dividing by 12?
3,300.
I got 558.5.
Wait, what?
558?
6697.8. 5 by 12.
Uh-oh. I'm sorry. I'm sorry, we've got a big problem. The big problem is this.
It's too big.
Text is way too big. The problem is that these units here that we wrote were in inches, but what about this guy?
Oh, so that's 60.
All right, let's make that 60. Try this again. So this is 60. So this should be 60x.
So it's 558.15.
No, no, no. So wait, what's 183 squared?
Oh, I see.
And then divide by 60. What do you get? What is it?
Oh, so now he's at 60.
Divided by 6.
So 60, 183.
46.5.
Oh, I get it. Okay, 183 squared divided by 60 is 558.
558?
Yeah.
Then divided by 12 is 46.
What is it? 46? 46.5 feet or 558 inches, but that's just x, right? So this is 46.5 feet plus 5 feet,
So that's 50.
and we end up with about 52 feet tall. About 52 feet tall, so big text is pretty big. Okay.
148. Got it.
Let's see. So I had another example like this, but I think I'm going to stop and I'm going to ask you to work on this worksheet that I have for you where you can try your own little examples and so forth. All right, so this is going to be the end of this video. Those of you watching, I hope that you got a worksheet from me and a tool belt. All right, and we'll see you next time.